This is a video on graphing linear inequalities. We're going to be looking at 6 examples today in which we'll decide where the boundary line should be, whether the boundary line should be solid or dashed, and then which side of the boundary line to shade to show where the solutions of the inequality are. Here we have y is greater than 2x minus 5. Because this is a greater than and not greater than or equal to, the solutions to y equals 2x minus 5 are not included in the solutions of y is greater than 2x minus 5. So solutions to y equals 2x minus 5 are not solutions for y is greater than 2x minus 5. However, y equals 2x minus 5 is the boundary line between things that are and are not solutions. Because it's the boundary line but is not part of the solutions, we're going to make it dashed. That will show us where the boundary is, but indicate to us this part here, that the solutions along that line are not actually solutions to the inequality that we're graphing. So first we'll focus on graphing y equals 2x minus 5. 2 being the coefficient of the x tells me that the slope is 2 over 1, and the b value of negative 5 tells me that the y-intercept is at 0, negative 5. So we'll start by graphing a point, which we know at 0, negative 5, and then we're going to go up 2 and over 1 to find our next point. So we'll keep doing the same thing. And remember we said that this is going to be a dashed line because the solutions along this line are not solutions of our actual inequality. So I've drawn a dashed line through there, and I'm going to put arrows at the end because this line does continue forever in both directions. The next thing we need to determine is whether to shade on the left or shade on the right, or in other words, to shade above or below the boundary line. To answer that question, I'm going to test a point that's on a particular side of the line. Whenever the line doesn't pass through 0, 0, I like to test the point 0, 0 to see whether it is a solution to the inequality or not. If it is a solution to the inequality, I shade on the side containing 0, 0. If it's not a solution to the inequality, I shade on the side that doesn't include 0, 0. So let's check. So if I wanted to see if 0, 0 was a solution to our original inequality, I'm just going to plug 0 in for y and 0 in for x. So on the left-hand side, we have nothing to simplify. And on the right-hand side, 2 times 0 is 0. 0 minus 5 is negative 5. 0 is, in fact, greater than negative 5. So 0, 0 is a solution to y is greater than 2x minus 5. That means that this should be part of the shaded side of the graph. So I'm going to shade everything over here on the left, or you can think of that as being above the line. That means that anything in this shaded part, okay, and remembering that the shading really will go infinitely off up this way and down that way. That means that anything in this shaded portion of the graph is part of my solution set. So here is a point at 0, 4, which will be a solution. Okay, so 4 is in fact greater than 2 times 0 minus 5, right? Because 4 is greater than negative 5. So that point is a solution. There's a point over here at negative 4 comma negative 2 that is also a solution because negative 2 is greater than 2 times negative 4 minus 5, right? Negative 2 is greater than, what does that come out to? Negative 13. So anything in this blue shaded section is a solution to the original inequality. Our next example is very similar. The biggest difference I see is that now we have a greater than or equal to. That means that solutions to the linear equation y equals 7/4 x plus 2 will be solutions to the inequality y is greater than or equal to 7/4 x plus 2. So when we graph this line, it will be a solid line. So we need to graph y equals 7/4 x plus 2. The The plus 2 part tells me that if I plugged in x equals 0, there would be a point at 0, comma 2. And 7/4 is our slope. So I need to go up 7 over 4. Well, if I tried to go up 7 here, I'd be off my grid. So instead of going up 7 over 4, we can go down 7 and back 4, because positive 7/4 is the same as negative 7 over negative 4. Okay, so I can go down 7. So from 2, I'm going to go 1, 2, 3, 4, 5, 6, 7. I'm at negative 5. Then I'm going to go back 4, which means to the left 4. 1, 2, 3, 4. Notice that going down 7 and back 4 gets me the same slope as if I went up 7 and over 4, okay? The slope between those is the same. And I can draw a solid line here because our original inequality said greater than or equal to, which means the solutions along this line are part of the final solution set. Then we need to test a point to see where the shading should go. We'll test our point 0, 0 because the line itself, the boundary line, is not on 0, 0. So 0 is greater than or equal to 7/4 times 0 plus 2. 0 is greater. This comes to 0. So is 0 greater than or equal to 2? No, of course not. 0 is less than 2. So this isn't true. So 0, 0 is not a solution. That means that we need to shade on the side that doesn't have 0, 0. So we're going to shade over here. There we go. Remember that means that this point here, negative 3, 4, is a solution to the original inequality. Negative 4, 1 is a solution to the inequality. Negative 2, positive 2 is a solution to the inequality. Negative 3, negative 2 is a solution to the inequality. So is anything along the boundary line. So for example, down here, negative 4, negative 5 is a solution to the original inequality. In the last few examples, we've had inequality written in what looks like y equals mx plus b form. This time we can do one of two things. Either we can rearrange this inequality into something like y equals mx plus b form, or we can use the intercepts to graph the boundary line. We're going to do both. I'm going to start with the y equals mx plus b form since that's what we did with the last two, and then I'll also show you how to do it with the intercepts. So if we had 3x minus 2y is less than 10, to put it in mx plus b form, we want to get y by itself. So I'm going to subtract 3x from both sides. It'll cancel out on the left, and I have negative 2y is less than 10 minus 3x. We're going to divide by negative 2. Now remember, one of your inequality rules is that when you divide or multiply by a negative number, the sign changes direction. So we now have that y is greater than 10 minus 3x over negative 2. So 10 divided by negative 2 is negative 5. Negative 3x minus 2 is going to be plus 3 halves x. And if I want to write that in mx plus b form, I'm going to have 3 halves x minus 5. So y is greater than 3 halves x minus 5. To my mind, switching it around like that has a lot of room for error, especially with the sign being flipped and then dealing with simplifying a fraction like this where we had to have 10 divided by negative 2 and then negative 3x divided by negative 2. I think there's a lot that could go wrong here and trip you up when you're trying to do a problem you could do another way. So I'm going to leave that final inequality that we got here, the y is greater than 3 halves x minus 5, and I'm going to show you a different method that we can use to graph this inequality. Rather than graphing y equals 3 halves x minus 5 as the boundary line, we could instead use 3x minus 2y equals 10 as the boundary line, and then we don't have to do the rearranging we just did, trying to solve the inequality for y. And the reason we can use this is because we can find the intercepts of the equation, where they intersect the x and y axes, by plugging in 0 for one of the variables. So if I plug in x equals 0, I can find the y-intercept. So I get y equals negative 5 when x equals 0, so there's a point at 0, negative 5. And then we can do the same thing to find the x-intercept by plugging in 0 for the y value. So in this case, x is going to equal 10/3, which is 3 1/3. So we have an x-intercept at 3 1/3, comma 0. So 3 1/3, 0 is going to be about here. So our boundary line goes right through here. Okay, and it's not going to be solid, but I want to show where it is and compare it to what we got when we solved the inequality for y and put it in mx plus b form. Recall that that was 3 halves x minus 5. Well, the minus 5 would tell us that we have an y-intercept at -5, which is the same thing we found when we solved this equation over here, plugging in x equals 0. And our slope is supposed to be 3 halves. Well, let's see. If we go up 3 over 2, that looks about right. We go through the point -2, +2, up 3 over 2 again, up 3 over 2 again. So the method that we used finding the intercepts got us the same line as the method of solving and putting it in y equals mx plus b form. Okay? And that makes sense, right? Anything that's going to satisfy that line should satisfy it, whether it says 3x minus 2y equals 10, or we've rearranged it to y equals 3 halves x minus 5. They're the same equation, they're just in different formats. So let's go back to the original inequality for a minute here. 3x minus 2y is less than 10. Is less than means that the boundary line needs to be dashed. Okay, it's not included in the solution set. So let's dash this. If you were doing this on a piece of paper, I recommend lining up a ruler, a piece of paper, some sort of straight edge along the 2 points that you've graphed and dashing along that straight edge so that your line looks a little bit neater than mine. The only thing we need to finish up now is figuring out which side of this boundary line to shade in. So let's see, 0, 0 is not on the boundary line, so we can use that. We'll plug in 3 times 0 minus 2 times 0 and see if that's less than 10. Well, 3 times 0 is 0, 2 times 0 is 0, 0 minus 0 is 0. 0 is in fact less than 10, so we need to shade on the left-hand side of this boundary line. Anything above, or if you want to say to the left of the boundary line, is a solution, but not anything on the boundary line itself. Now, some of you might be confused looking at the fact that our original inequality here said less than. You're probably thinking, well, less than, I need to be shading below the boundary line. Let's think about what happened when we put this in mx plus b form. We got that y was greater than 3 halves x minus 5. And that sign flipped because we divided by a negative number. So if it's in y equals mx plus b form, the rule of greater than gets shaded above and less than gets shaded below does apply. But if it's in what we call standard form, where the x and y are on one side and the constant term is on the other, that rule doesn't apply in the same way. So it's always good to just plug in 0, 0, see if it's a solution or not a solution. That is the best way to determine which side you should shade on. Our next example is in the same format as the last one. We have the x's and y's on one side and some constant term on the other. This one I could figure out the intercepts, but I think it might just be easier if I added y to both sides, and then I would see that x is greater than or equal to y, which I could write as y is less than or equal to x. Because it's or equal to, I'm going to have a solid boundary line, and the boundary line is just described by y equals x. So if you want to think about that in mx plus b form, that's y equals 1x plus 0. So 0 is the y-intercept, and it has a slope of 1. So we're going to go up 1 over 1, up 1 over 1, etc. I can also go down 1, back 1. Y equals x is the line that goes straight through the origin and has a slope of 1. And I drew that terribly, but I'll leave it to you to use your imaginations that that is a straight line with a slope of 1 going through 0, 0. The last thing we need to figure out is which side to shade. And I was just saying on the last problem, oh, you always plug in 0, 0 and see which side you should shade. Well, that doesn't apply here. This is the one special case where that doesn't apply because 0, 0 is on the boundary line. It's not going to tell us which side to shade because it's not on a side. It's in the middle. It's in between the sides. So we need to pick a different point. And so you can just pick one that's pretty easy. Okay, I could have picked this point over here, this point over here, this point over here. I'm choosing, however, to work with the point 1, 0. Let's plug it into the original inequality. So my x value here is 1, so I'm saying 1 minus my y value of 0 is greater than or equal to 0. Well, 1 greater than or equal to 0. Is that true? Yeah, that's a true statement. So 1, 0 is a solution. That means that this is the shaded side of the equation. I've got 2 more examples for you today. Here we're working with y is greater than or equal to 4. There's no x in this inequality. We could think about there being an x, but what would x have to be multiplied by to be equivalent to the original inequality? Well, it would have to be multiplied by 0. 0x would cancel out and just be 0, and we'd be left with y is greater than or equal to 4. So if we think about that as 0x plus 4, then our slope is 0, or 0 over 1, and our y-intercept is 4, 0, 4. So if our y-intercept is 4, and then we have a slope of 0 over 1, well, that means that our rise is 0. It means we don't go up any at all, but we go over 1. And then again, we don't go up any at all, but we go over 1. We can do the same in the other direction. And we can go up nothing and then back 1. So in fact, our boundary line in this case is a horizontal line. And it's a horizontal line through y equals positive 4. Okay, it doesn't matter what x is. X can be negative 4, so we have negative 4, 4 as a point. It could be negative 2, 4. We could have 3, 4. We could have 10 billion, 4, right? And that's not where 10 billion is. But any x value, it doesn't matter. Y doesn't care what the x value is in this case because y doesn't depend on x. Y just needs to be greater than or equal to 4. Speaking of that greater than part, we need to figure out which direction to shade. Well, is 5 greater than 4 or is 3 greater than 4? Well, 5 is, of course, so we need to shade above. Y has to be greater than or equal to 4, so we need to shade above the y is equal to 4 line. Our last example for the day says x minus y is greater than 2. I'm going to use the intercepts that we used several problems ago to graph the boundary line x minus y equals 2, right? That's the boundary line. And in this case, it's going to be dashed because we don't have an or equal to in our original inequality. So if I plug in 0 for x, I'm going to get that negative y equals 2, which means that y equals negative 2. And if I plugged in a 0 for y, I'm going to get that x equals 2. So when x equals 0, y equals negative 2, and when y equals 0, x equals positive 2. So we have points at 2, 0, and 0, negative 2, which means that between them we've got a slope of 1, and we can connect our line here, making it dashed, of course, because this was a greater than but not greater than or equal to inequality. Last but not least, we need to decide whether 0, 0 is part of the solution or not. So 0 minus 0 is greater than 2. Let's see. Well, is 0 greater than 2? No, that's not true. So 0, 0 is not a solution, which means we need to shade below the boundary line. And that's our graph of the solution of x minus y is greater than 2. So when you're graphing linear inequalities, the first thing to do is identify the boundary line. That's going to be where you find points either through y equals mx plus b form, or you use the intercepts. And remember, the intercepts is where you plug in 0 for x and then 0 for y and see what the corresponding x or y value is. Once you know some points on your boundary line, you're going to have to decide whether it's dashed or solid. To be solid, you'd have to have a greater than or equal to sign or a less than or equal to sign. And to be dashed, you'll have a greater than or a less than. And it's that or equal to part that tells you that the boundary line is included. The last thing you'll need to do is determine which side you need to shade. Usually you can plug in what point? 0, 0. Okay? Usually you can plug in 0, 0. If not, okay, and remember that happens if the boundary line goes through 0, 0. If not, you can pick any point not on the boundary line. Okay? 0, 0 is usually the easiest, but if it happens to be on the boundary line, you can pick something like 1, 0 or 0, 1 to work instead.